Hi, good morning. Well, my name is Salvador Pacheco. I work in the Department of Control Systems. Well, I work in the Department of Control Systems with my PhD project. I'm going to show you now, like, some of the one of the parts that I was doing working on my PhD. I'm going to give you a little bit of a background of what we're doing in the department. Basically, we're working with mobile robots, and the aim of the whole team was to be able to deploy uh, a certain amount of robots in a partially known environment to go around, perform a slam, do mapping of the environment, and come back safe to the place where they were deployed. So part of that work that represented the need for us to be able to recognize some shapes inside of the environment. We're very restricted in terms of the equipment that we can use. We're not able to take a very sophisticated LiDAR or anything like that, or any system like that to get to the information. So we have to find a way for us to guarantee the detection of shapes, primitives such as vessels, containers, pipelines. So that's pretty much the background of what we did in the team. Together with my colleagues, we managed to pretty much get something working. And this is just, I'm going to talk about the detection of these shapes that I'm talking about. So well, this is the outline of the presentation. I'm going to give you a brief introduction, which I pretty much did already. Interval basis, I'm going to go very, very fast on that because I think pretty much everyone is an expert in that now. The shape parameter estimation that we used and how we robustify against the outliers and noise in the point cloud. I will show you some case studies with some comparisons against the state-of-the-art techniques such as RANSAC, pretty much. That's the one that is used in the literature, and some conclusions. So great, well, as I mentioned earlier, the final task of any mobile robot system is usually to analyze the data gathered through the mapping environment, to the moving around the environment. You have to analyze what's inside, you have to analyze from different sources, any kind of sensors such as heat, image, clouds, everything you can, humidity as well. From our case, we're going to analyze data gathered from a geometrical point of view, so we have to detect and characterize these objects. So, as I mentioned earlier, due to the restrictions that we had, we need to make a guaranteed robust model detection. For this thing, we have to consider that, well, in this particular case, as you can see in the image, we use the sensor Kinect for getting the 3D information and the RGB data. This sensor is cheap, it's very useful, it's being used for many research institutes because it's easy to get, it's hacked already, you can get information pretty much easily. But it's got some inconvenience, which is you can have several types of noises, such as you can have noises coming from the surfaces that you are measuring. You can get it from the angle of attack, some surfaces, even if they are not bright or anything, but still the angle affects. And of course, the occlusions in the data can cause some problems. There have been some papers related with the modeling of the noise inherent to the sensor, but still they make a lot of assumptions to get this statistical error modeling. So this is why, well, the why of the interval methods is because we don't need making assumptions on the distribution of the measurements when we're getting the information. And it's been proved to be convergent mathematically. Well, as I said, I'm going to go pretty fast with this. Everybody knows what interval methods is. Just for the sake of the nomenclature, probably it will be worth to go through this. We define the real interval as a variable x in this case, in brackets. You know, we can do intersection, union, some basic arithmetics, as well as elementary functions. That's pretty much known by everyone. And we define the box as the cross product of these intervals in n, Rn. So, to solve this, we have to use the constraint satisfaction problem, which is defined by the function shown. And having a function and a set of parameters, it's possible to define the constraint satisfaction problem in this manner. Okay. having in initial domains for the parameters that we're looking for. So as we know, contraction is a way for us to solve the constraint satisfaction problem. We know everything that everyone that we have to have contractness and correctness, which is that we enclose the correct solution, and every time we apply this contraction, we decrease the size of the box. So of course, I can show you this image. If more accurate solution we have, most of the times, depending on the function that we're using for contract, we need to use the CV algorithm to do some bisections around the initial boxes. Okay, so this parameter estimation has been proposed before in a two-dimensional space by Professor Luke to determine the parameters of, for example, in this case of a circle. So basically, we want to determine the parameter speed that define the circle that is determined by the measurements gathered by any sensor. It can be an image, it can be a photograph. Of course, we know that those measurements have a noise bounded by some boundaries, upper and lower boundaries. So this problem can be characterized in this manner, which represents the parameter vectors, the intersection of all the parameter vectors that comply with the constraint of the function we are trying to fit. So again, as I mentioned earlier, we have different source of noises, so we have to take it into account. For that, we have to use a relaxation procedure, which allows us to neglect the points that do not correspond to our shape. So that basically here we have a Q relaxation diagram, which allows us to neglect based on a parameter, which is, for example, here, based on the parameter Q, which is in this case for image A is 3, knowing that we have n boxes, we can neglect the rest of the value of the boxes that do not intersect. That intersect 3 at most in the set we have. So having that, the equation that I showed you before for the detection of shapes can be represented in this form using the Q relaxation. Okay. I'm going to go to the case studies that we did. We used for this, as I said, the Kinect sensor for getting the information. We used some pre-processing of the cloud. By pre-processing, I refer to do some segmentation only. We didn't apply any filtering or anything to the clouds that we used. So you just got the raw data, do some segmentation of the ground, because that's can be easily done. Because you know your robot is moving around, you can neglect these parts and get what you're interested in. So for that, we have to define a constraint satisfaction problem for each one of the shapes we're trying to fit. So for the 2D circle, I think it's pretty much obvious. We have this implicit form in here. And we got the following results. This is simulated data for the 2D case. For the 3D case, I will show you some real data as well. Something very interesting that we had to cope with is with the fact that we may not have fully depicted shapes with the data that we are dealing with, because particularly in the real case when the robot is moving around, most of the times, I will not say all the time, but most of the times, you are not able to appreciate the shape like fully around 360 degrees around it. So we have to cope with the lack of information depicting that particular shape. So for example, in this case, we tested it with a 2D case. As you can see in this image, we have points that depict the whole shape, and this one is just 3/4 of the shape. We have only half, we have less than half. I think it's like around 1/3 of the shape in here. Actually, it's 30% of the real points depicted in the circle. As you can see, we always, this is the parameter, the true parameter vector, right? So after doing our method, as you can see, we always fit inside of the solution is enclosed inside of of the interval that resulted. So we have some comparison as well, as I mentioned earlier, with the ransack method. Uh, I don't know if I will try to explain this graph. I try to put everything in the same. In the left y-axis represents the mean square error, and the lines with regards to that axis, it's the blue one and the red one. So as you can see, we have the mean square error is pretty much very good with the intervals. Actually, as you can see, the more we have with the outliers, we go very well with the outliers in our technique. The only thing is that yes, interval methods, as well as mentioned earlier, right, yesterday, takes longer to converge. In this case, ransack is way much faster. Okay. So I apply the same technique for the plane, which is represented in a Hessian form. So this is the original data. We just got a simple plane in 3D. This is so the gray plane is the one that is fixed on top. Again, we apply several sources of noise. We increase the amount of outliers to test our algorithm. In reality, actually, when we tested these algorithms in real walls, real floors, we don't have that amount of outliers. This is more smooth, even without doing any pre-processing. But still, we wanted to test it against the worst case scenario. For example, in this case, we have a set of like signs and boxes in different angles. And we applied this algorithm recursively, and we were able to find the parameters of these planes. Well, here are the parameters that we found in each one of the images that I showed you before. In this last one, in the 12A, B, C, and C, we don't have a ground truth because it's the actual real data, so we just gather it. But by appreciation, by eye of the shapes, when we're doing the fitting, we can tell that it's a very good model. Again, here is a comparison that we did. As you can see, something that I forgot to mention, we used for doing this comparison in particular, we cannot use the interval itself, we use the midpoint of the parameters that we got. So as you can see, the mean square error of the interval analysis is always smaller than the one in ransack, again for the midpoint. But again, we have this times larger still. Okay. So we did the same for the sphere, again, fully depicted with all the points. And this is just 1/3. We did several tests in between, but I didn't want to put them all. And again, we're able to pretty much get a good shape. This is like a football. We just took an image of it, and again, we get parameters of it. And there you go. We have still the parameters inside of the vectors are enclosed, parameter vectors enclose the real solution. The same here, we have the comparison that we did with the mean square error and ransack. One of the things that we were really focused on, more than in spheres, because of the nature that I'm talking about the application, is pretty much cylindrical shapes, which is pipelines and vessels. So for that, we have this representation. There are quite a few representations of the cylinder. How can you express it? It can be parameterized, the form. But we did it in a vectorial way, so we can come with this is the representation. Basically, what we need to define a cylinder in this form. We need an axis, the central axis of the cylinder, a point over the axis. We need to know the radius of that cylinder. We will have an infinite cylinder still, but doing some manipulation of the information that we got, we can define the top and bottom leads. So for that, we can define this constraint satisfaction problem. But we have, in this particular case, we have 7 parameters to define. So we tested it, but due to the nature of CVA, it was taking too much time. So we decided to do something to reduce the dimensionality of the parameters that we're looking for. So what we did basically is using principal component analysis, we defined the axis of this cylinder. With that axis, it's possible to define a plane using as a normal this vector. And then we just project this point on top of that plane, which you can see here in red. Basically, that's a projection of that vector. That becomes a two-dimensional problem of finding a circle. So that's how we define the radius. And we have the axis, and we can define the whole cylinder using that approach. As I mentioned earlier, the length of that cylinder can be defined, well, there are several ways, but what we did is basically we projected the points over that vector that we defined, and we just find the maximum and minimum point on top of that line. Again, we tested this approach using, in this case, it's like 1/3 of the surface of the cylinder, which is a very, very common problem, particularly in pipes attached to the walls and stuff. So still we have good results. And again, when we tested in real data without, because in here we can see we have quite a lot of noise, 20% of noise in this case. We tested it against more, and so we have good results. And we tested in real data. This is pretty much like the scenario that we have in a vessel. We don't even see maximum 40% of the whole surface, but still we were able to detect shape in a pretty good manner. Okay, so these are the parameters that we found. And in this particular case in the cylinder, as you can see, the interval analysis showed us very good results in comparison even with the ransack. So when the amount of appliers goes really high, the error using the common typical approach of ransack goes quite high, while the interval analysis remains pretty much the same. Again, the time is a factor, but there's a trade-off between accuracy and making fast. Well, we show this method that proves to be convergent in the different circumstances. We tested it, and we always got good results, even with synthetic data, very noisy synthetic data, and with real information. This travels to outliers. It's tested, and it's convergent even when the shape is not fully depicted by the amount of points immersed in it. Well, in the future, we're trying to. I was actually having a talk with Professor Irina about finding a better way to detect the cylinder without taking into account the PCA, because we try to avoid that part. We actually had a talk yesterday. Hopefully, we'll get something good about it. Of course, we want to combine more shapes, but that we need a more sophisticated kind of isolation of shapes inside of a single cloud. Something we'll probably have to look at it. Also, we have to consider other representations of this information. We can use in the future mesh, polygons, normals included to this. Perfect. And I don't know, in the future, probably would be very nice to implement it in some sort of parallel processing, so we can do these things faster and in a real time, so we can actually implement it in the robotic system that we already have. Thank you very much.
Salvador. I would like to know how much it takes for the cylinder using the interval method.
Time?
Yes, just an idea.
It depends, but it takes like 1 to 2 seconds. But my computer was really bad, but yeah.
It's still okay.
Yeah, it's still fine. Yeah. But it's not like too long. When we use this approach, when we're using the 7 parameters, actually I left it for 40 minutes and we still didn't get any good results.
Yes.
So that's why we do this.
And when you use the ransack approach, you will have to select randomly some points, but after you have to find the corresponding parameters. So maybe you have to solve the ransack for the cylinder is not so easy though. How do you do for the ransack?
Oh well, basically inside of the for the ransack is like a algorithm that includes internally a minimum square. So we basically select 3 points in this case, and then we try to fit it to a certain amount, to a cylinder. Then we measure the error. If it's not good, we have to iterate again, and then we use some probabilistic techniques to see how many iterations will be great.
It occurred to me when you showed the part of the sphere and the part of the cylinder. So you said you looked at the third of the sphere. Does it matter what shape the noise is? Could you make the noise be the shape of one of the other shapes that you could detect? And so, you know, the part of the sphere with a shape, with a noise is the shape of a cylinder, and then you apply the sphere first, and then so you apply the thing subsequently.
Yeah, for that it's basically like we need to use an algorithm for hierarchically detect shapes. I mean, that's what you mean. Like,
well, hierarchically it would be more difficult, but just sequentially, it would be an interesting experiment to make the noise in the shape of something else, or even in the shape of a sphere.
Yeah, it actually will be good. Probably what would happen is it will detect the shape with the higher amount of points depicting that shape. That's my feeling. But yeah, it will be tested.
Well, how will you decide about this realization parameter?
Well, what we're doing now is we do it sequentially. If you have an idea of how much noise you might have, you can define it as a parameter in the beginning of the program. And if it's not converted, if you don't find a solution, then set you'll carry on increasing it until you find a solution. So you don't have to know in advance yet.
Okay. Questions?